Hello everyone. In this example we are asked to determine if the following planes are intersecting or if they are parallel, and depending on that we'll have to then solve another set of questions. So if they do intersect, we want to find the angle between the planes as well as the symmetric equations for their line of intersection. And in the case where the two lines are parallel, we're going to try to find the distance between those two planes. And so our first plane is given by this scalar equation, x plus y plus z is equal to 1. And our second plane is given by the second scalar equation, x minus 2y plus 3z is equal to 1. So the first thing we have to do to figure out which set of problems we're going to try to solve is determine if the planes we are given are parallel or intersecting. And so we do not need to graph these two planes to figure this out, but some visualization will help us conceptually. And so if we think about the picture or visual of two planes being parallel, it's going to look something like this, right? They're going to have the same tilt, angle, or slope on them. And remember, planes have their kind of tilt or slope or orientation uniquely determined by that normal vector. But if we have two parallel planes and compare their normal vectors are also going to be parallel to each other. And that's a really important observation that we need to use here. And so parallel planes are also going to have parallel normal vectors, and we can determine if a vector is parallel to another vector just by checking to see if the one vector is a constant multiple of the other vector. So can we take that first vector and multiply it by 3 or negative 1/2 and turn it into the other vector? If it's possible to do that, then those two vectors are parallel. So to determine if the two planes are parallel or not, we need to see if their normal vectors are parallel or not. And so what is the first plane's normal vector and what is the second plane's normal vector? We'll call them n1 and n2 respectively. Remember, the kind of general form for a plane looks like ax plus by plus cz plus d is equal to 0. Well, in this case, we have the constant moved to the other side, but that is not too important here because in order to identify these normal vectors, those components a, b, and c, we just look at the coefficients in front of our variables x, y, and z. So our first plane is going to have a normal vector with components of 1, 1, and 1, since those are the coefficients in front of x, y, and z. And our second plane is going to have a normal vector with components of 1, negative 2, and 3. And so we can clearly see that these two vectors are not constant multiples of each other. We cannot just take the first vector and multiply it by like negative 2 and turn the first vector into the second vector. Because these vectors are not constant multiples of each other, they are not parallel. These vectors are not parallel since the first normal vector is not some constant multiple of our second normal vector. And so that means our two planes here are not parallel, so they do not have the same tilt, and since they are not parallel, they therefore must be intersecting planes. So when two planes intersect in three-dimensional space, the set of points that are common to both planes is the line of intersection between those two planes. So two intersecting planes are always going to form a line in three-dimensional space. So one of our goals now is to find that line of intersection between our two intersecting planes, but we're also asked to find the angle between our two intersecting planes. And so the first question we're going to try to tackle here is what is the angle between these two intersecting planes? And so what we have here are two intersecting planes, and we're trying to find the angle between them. And if we take our intersecting planes and view them from the right angle or from the side appropriately, it's basically going to look like two intersecting lines. So maybe from the side profile, our first plane looks like this, and our second plane perhaps looks like this. Well, there's really two different angles we could look for here, this acute angle between our two planes or this obtuse angle between our two planes. And we're trying to find the angle between two intersecting planes. We're always looking for that acute angle between the two planes. And so this angle between our planes is like the difference in the tilt between our two planes. Well, we know parallel planes are going to have parallel normal vectors. And so if our planes are not parallel, then the difference between their normal vectors is going to describe that difference in tilt between our two planes. And so the idea is if we were to rotate our green plane backwards this angle of theta, it would make our two planes parallel and their normal vectors would line up. So if we reverse that process, we can pretty clearly see that the angle between our two normal vectors is going to be the same as the angle between our two planes. And that's the best way to find the angle between two intersecting planes is to find the angle between their two normal vectors. And so the angle between our two intersecting planes is the same as the angle between their two normal vectors, and we already know how to find the angle between two vectors using the dot product formula. So if we use n1 dotted with n2, we'll be able to compute that because we know the components of n1 and n2. We also know that we can compute the dot product by taking the magnitude of n1, multiplying that with the magnitude of n2, but then also multiplying that by cosine of theta, where theta is that angle between our two vectors and the angle between our two planes. So we can solve for the left-hand side of our equation, find the magnitude of our two normal vectors, and then solve for cosine of theta. Another way to do it that's pretty popular is to rewrite this formula as cosine of theta is equal to n1 dotted with n2 divided by the product of the magnitudes of the n1 and n2 vectors. All right, so what is n1 dotted with n2? Well, remember, to compute a dot product using the components, you multiply the corresponding components together and then take the sum of those products. So multiplying the first components gives us 1 times 1, which is 1. Then we add to that the product of the second components. That'll give us 1 times negative 2, which is negative 2. Then we add to that the product of the third components, which is 1 times 3, or 3. So our numerator is the dot product between n1 and n2, and that's 1 minus 2 plus 3, which will work out to 2. Well, our denominator is going to be found by finding the magnitude of our two vectors and multiplying them together. So remember, to find the magnitude of a vector, you have to take the square root of the sum of the squares of the components of that vector. So for n1, that's going to look like the square root of 1 squared plus 1 squared plus 1 squared. Then we have to multiply that by the square root of the sums of the squares of the components of our n2 vector. So the magnitude of our n2 vector is going to be the square root of 1 squared plus negative 2 squared plus 3 squared. Let's see, in our first little square root, we have 1 plus 1 plus 1, which will give us the square root of 3. And then in our second square root, we're going to have 9 plus 4, which is 13, plus another 1, and that'll give us a 14 underneath that second square root. So we know cosine of theta is equal to 2 over the square root of 3 times the square root of 14, or we could write that as 2 over the square root of 42. It doesn't matter, it's all equivalent. In order to find our angle theta, though, we're going to need to use our inverse cosine function. And so by taking cosine inverse of 2 over the product of the square root of 3 with the square root of 14, a cosine inverse is going to give us a value of about 72 degrees. So the angle between these two intersecting planes is going to be approximately 72 degrees. And so that solves the first part of this question. We found the angle between our two planes to be theta, and that's approximately 72 degrees. The second part of this question we still have to figure out, and that's finding the symmetric equations for this line of intersection between our two planes. And so we still have to finish off the second part of this example, and that's by finding the symmetric equations for the line of intersection between our two planes. And so now we're tasked with finding the symmetric equations for the line of intersection between these two planes. And an important observation that's going to help us do this is to recognize the line of intersection lies in both planes. And that may seem like an obvious statement, but it's an important one to make. So the line of intersection is definitely going to be in both of our planes. Otherwise, it can't be the line that contains all the points that are common to both planes. So what we also know is the normal vectors to our two planes. And if we take any vector that is in our plane and compare it to the normal vector for that plane, it has to be orthogonal to the normal vector. Right? That's kind of the point of the normal vector, right? It's orthogonal to every vector in the plane. And so our line of intersection is in both planes, and so that means our line of intersection has to be orthogonal to both of these normal vectors. So the line of intersection, or really the direction vector for the line of intersection, has to be orthogonal to both of the normal vectors. Because the line of intersection is orthogonal to both of our normal vectors, we can use the cross product between our two normal vectors to find the direction of the line of intersection, right? Because what does the cross product do? It takes two three-dimensional vectors in, and then it finds a vector that is orthogonal to both of the input vectors. We're essentially just kind of reversing that process here. We know the line of intersection has to have a direction that is orthogonal to both n1 and n2. And that's because the line of intersection is in both planes, and any line or vector in the plane has to be orthogonal to the normal vector for that plane. Because our line of intersection is in both planes, it has to be orthogonal to both normal vectors. So we can create this orthogonal vector by taking the cross product between our two normal vectors. So the direction of our line is going to be given by the cross product between our two normal vectors. Once we compute that, we have the direction of our line. The only other thing we need to create the symmetric equations for our line is a point that our line goes through, which we'll also be able to find using the equations of our planes. All right, so let's go ahead and call the direction of our line the vector v. After our discussion, we know the vector v, or the direction of our line, is going to come from the cross product between the normal vectors for our two planes. And I've gone ahead and set up our 3x3 determinant to evaluate this cross product. So the first row is our basis vectors I, j, and k. The second row are the components of our n1 vector, and the third row is the components of our n2 vector. So to compute the I component, we look at the right diagonal that starts from I and subtract away from that the left diagonal that starts at I. The right diagonal will give us 3. We have to subtract away from that the left diagonal, which will give us -2. So our I component is eventually going to be 5i. All right, for the j component, we repeat this process, take the right diagonal that starts at j, and then subtract away from it the left diagonal that starts at j. So the right diagonal is going to give us the product of 1 and 1. Then we have to subtract away from that the left diagonal that starts at j, which will have us multiply 1, and after wrapping around, 3 together. So that second component will look like 1 minus 3j, or -2j. And for the kth component, we do this one more time. The right diagonal that starts at k is going to give us -2. And we have to subtract away from that the left diagonal that starts at k, which is going to give us 1 times 1, or 1. So piecing those together, we see our k component is going to look like -3k. So let's make a note of this vector that we just found, v. V is the direction of our line, and that's the vector with components of 5, -2, and -3. So to finish constructing our line of intersection between our two planes, we now just need a point that is on the line of intersection. So let's go ahead and make some space on the board to find this point that is on the line of intersection. And so what we know is that any point that is on our line of intersection has to satisfy both equations for both planes. And so I think the best way to go about doing this is by plugging in a value for one of your variables, like z equals 0, y equals 0, or you could do a non-zero value like x equals 3. And that'll turn your 2x3 system, that is your system of 2 equations and 3 variables, into a 2x2 system that we can solve. We do have to sometimes be a little bit careful in choosing a value to plug in for one of our variables, and that's really only if one of our planes is like parallel to the xy plane, the yz plane, or the zx plane. And that'll also kind of show itself and be pretty apparent because one of those variables will be missing from the equation for our planes anyways. So what will pretty much work every single time is pick a value for one of your variables, plug that value into both equations for each plane, and then solve the resulting 2x2 system that we get out of that. So let's go ahead and let z be equal to 0. So kind of visually what we're looking at when we set z equal to 0 is the graph of z equals 0 is just the xy plane. So we're really figuring out where on this line of intersection between our plane does that line of intersection intersect the xy plane. So after we have set z equal to 0 to put ourselves on the xy plane, our first equation is going to turn into x plus y is equal to 1 because z is 0 when we're in the xy plane. And our second equation will turn into x minus 2y. Well, now we can solve this little 2x2 system very quickly and easily using the elimination method. Just subtract the second equation from the first equation. The x's cancel each other out. We have y minus -2y, which will give us positive 3y. And then on the right-hand side, the 1 minus 1 gives us 0. So we can see from this that 3y must be equal to 0, which tells us y has to be equal to 0. So we have z is equal to 0, y is equal to 0, and now we need to find x. And we can use either equation to help us find x at this point. But regardless of the equation we try to use here, when we plug in z and y both equal to 0, they simplify very quickly to tell us x is equal to 1. And so our point of intersection is going to be the point with coordinates of 1, 0, and 0. And so now that we have the direction of our line of intersection as well as one point that that line goes through, we can put that information together to create the symmetric equations for our line of intersection. So remember, the general form for the symmetric equations for a line are going to look like x minus x naught over a is equal to y minus y naught over b, which is at the same time equal to z minus z naught over c. All right, so x naught was 1, y naught was 0, and z naught was 0, and a, b, and c are 5, -2, and -3 respectively. So putting that all together, we see the symmetric equations for this line of intersection between these two planes is going to look like x minus 1 over 5. That has to be equal to y minus 0, or just y, divided by -2. And this has to also be equal to z minus 0 over -3, or just z over -3. So we have finished this example off. We found the angle between our two intersecting planes was about 72 degrees, and the symmetric equations for the line of intersection between our two planes looks like this. X minus 1 over 5 is equal to y over -2 is equal to z over -3.